Okay, we can get started. Thanks everybody for joining and for the patience getting the recording set up. Our volunteer today is going to be talking about Megablocks, which I've been very eager to look into for a while now. So, yeah, I'll hand it over to you.
That's right. Thanks. Thanks for having me. This is a cool algorithm I've been working on the implementation side for a while now. And so the way the paper connects and the actual implementation connects is something I want to talk about today. I have some slides. This is the paper right now I'm showing on the screen. It's really cool. It's written very sort of formally. And this is my understanding, when they started working on this, they were essentially they were motivated by MOE. They wanted to make sure they can route the tokens to experts efficiently. Each expert being just a matrix multiplication, but it's not trivial at all, sort of how to put these tokens together and how to, use actual linear algebra libraries to do this. They start with MOE. They talk about how to construct essentially an entire MOE layer, but then they deep dive into how you can compute this and how you can represent this in math and then finally in programming. So what I wanted to do today, actually, let me switch slides, is start with this context of the paper and what they were trying to do. But
Wait, it says
if
the
you guys,
stream ended. I think you need to reshare your.
no, that's right. I'm just switching between windows.
Oh,
My monitor's quite wide, so I want to do window by window.
okay.
Let me see. Give me 1 second.
No worries.
Uh, okay, cool. So the presentation I wanted to talk in this presentation, I want to talk a little more about ragged dots specifically. This is what we've been calling it sort of internally. NVIDIA has its own name, say group matmul. Megablocks obviously is an algorithm name. And then somewhat confusingly, maybe the paper uses CK, like Megablocks, and the algorithm in the JAX repo uses X. So a little all over the place. Um, but again, coming back to this context, they read the paper and they're really interested in how to perform this computation efficiently. And there is a lot of previous work on, in general, sparse computations. If you talk about fluid dynamics computations, or if you talk about like um, manufacturing chips, a lot of the math there ends up being lots of very large sparse matrices. The problem is that those representations tend to be element by element. That's very unfriendly to most accelerators. NVIDIA has been experimenting with stuff like CSC and CSR, which are these sort of older, yeah,
I think Kunjin needs
okay,
to
these are
mute
the,
his mic.
yeah, no worries. These are these older representations, and they essentially lay out how each element is structured. The acronyms themselves are somewhat of a, like, they're just more efficient representations. The canonical representation of sparsity that you can think of is just um, I have some elements in a list, and then I have two coordinates for them. Just the coordinate x and coordinate y for a matrix. CSC and CSR compress respectively a column or a row, so that you end up with approximately just a single index, and then an integer representing just how many elements there are in a column. But again, what happens is in a normal accelerator, you don't really want to deal with these elements. Having an element here and there is just would be really bad for performance. And we're trying to get the most out of the chip. So in the paper, they're very explicitly thinking about this. And instead, what they're saying is that maybe you can come up with a block sparse representation. So instead of thinking of it element by element, if I can have a block in my sparse matrix, but the block is fully dense, and if the block is large enough that the accelerator can make full use of it, then it's going to be okay. The details specifically of the representation are very similar to how you represent the scalars, the sparse scalars. So the CO representation is the easiest, and you can just store the block and its origin offset in a two list of coordinates for 2D. CSR does a similar thing but compresses the row representation. How it works in practice is that You still need two lists for the x and y coordinate, but you go to a little bit of a different representation. You go to a single list of, say, just the y coordinate, and then you go to a much shorter list that describes how many elements there are in particular row. Um, this is a bit of a gain. It definitely cuts down on the amount of memory you need for representing the matrix if you're talking about scalars. But I think even when they were writing a paper and they were moving to this block sparse representation, the amount of data stored in each dense block was much larger. And so as I'm going through this, I'll actually show you that the implementation on TPU uses the CO representation uh, mostly. So as these representation evolved and as they were experimenting with the actual implementations, like they sort of explored all the options, in a very research-like fashion. So the motivation really for them was the MOE block, and what they wanted to do is that this is a general representation, and when a paper lays out how to do this efficiently, it essentially also says how to do this efficiently because this is a simpler representation. Um, they, instead of having these equal sized blocks, they chunk them up even more. And this is as efficient as possible. So when it comes to the history of this, you have the motivation, which is the MOE part, which is we have this representation, we have experts, we have tokens per expert. The token might be imbalanced. And then we have the actual implementation, which is the actual base routine, which is what they were interested in implementing at TPU. These representations are close. The one on the bottom right is the more general one. So if they can implement this one, they have successfully implemented a routine, an efficient routine for this. Um, so the possible approaches that you can do this, you can do here is if you have a different number of tokens, you can pad these blocks of tokens to the maximum size, which tends to be memory inefficient. And this is the figure in the middle. So you end up with some number of tokens per expert, but it might vary. So you just pick the largest size, largest block size, and you end up with something that is bigger. If your routine and the accelerator is compute bound, this might not be that bad, but you're still wasting memory and you still need to relay out a lot of this stuff. They were looking for something closer to this. They were actually looking at very general Palace implementations of blocks like this. The alternative, though, is that you can also loop over individual rows, individual tokens. That was not a non-starter from the beginning because accelerators deal with this very badly. If you want to take a single row and multiply it by a matrix, the resulting product and the left-hand side are just so so not square that it's quite bad for the matrix multiplication unit on the TPU and GPU recently with this sort of hardware convergence. So there were a couple of decent approaches that they could try on GPU, and a lot of the world uses GPU, and they also wanted to make sure that that works. So what you can definitely do is use NVIDIA libraries and talk about each expert separately. A lot of MOE kernels actually to this day do this, and it's quite efficient. GPUs are sufficiently dynamic. You have sufficient number of SMs on the GPU that you can talk about just giving one expert to one SM and have it loop through the rows within the expert. On TPU, though, this didn't work. And this approach really relied on either writing a good C++ implementation that dispatched these libraries in C++, or more recently with, say, PyTorch, the better CUDA graph support. So it was a good approach, but you could essentially do better. And on TPUs, you could definitely do much better because TPUs weren't quite as good as this high level of dynamicism. So a super cool implementation Palace, and if you want to check out specifically the TPU dialect of Palace, is the prefetch scalar grid. And what that means is instead of looping through a two-dimensional grid of a fixed size, you only want to visit some blocks. This essentially goes back to the slide where these blocks are here, and all the gray ones are assumed to be 0. So this grid is imaginary. This actual data layout, this stuff lives somewhere else. Maybe there's an individual pointer to each of these blocks, but your Palace grid still benefits from being square. So what do? You design this schedule that essentially says load the block number 0, then load block number 1 and skip this work, then load block number 1. And if you do this, if you do the second block, when it comes to loading, there is no memory bandwidth. The pipeline just doesn't load the additional block. It's just already loaded. The key here is that as I'm working on the 0th block, I'm going to the next one where I'm skipping the work. I already want to start prefetching the next one. This is the prefetch part of the scalar grid spec. You're essentially trying to fetch the new memory for the new work, even though you're only going to start going there in a while, as soon as possible. And if you want to start with these prefetch scalar brick programs, this is by far how you would write those from the beginning. So again, a super useful routine. This is like the first time that the TPUs in Palace can be programmed in a very dynamic fashion. Um, the way you typically implement this is if you've worked with Palace and if you've worked with block specs, you have to provide a lookup lambda, which talks about which memory to load next. And what you could just do is pre-compute the actual lookup tables in Palace, and your lambda now has access to those. So it goes from a grid iterating over ij and your indices being ij for each individual tile of your program to the ij indices actually indexing into this pre-compute schedule. Um, you can actually re-implement this yourself. So if you want to go deeper into Palace, you can look into different types of memory. And here's an example of how you'd implement this the regular Palace program, one that has a very static grid, iterating one by one. Um, it's a very cool find, and this is really the key tech, the key DSL feature in Palace that you can really start talking about sparsity. Um, so now I want to switch to the modern Megablocks, the X implementation, and a lot of the couple next slides are going to be TPU specific. This is mostly because a lot of these challenges are a little more exacerbated on the TPU than on a GPU. It could be a little more dynamic. But realistically, the improvements you come up with here on TPU, they quite easily translate to. And so we've been talking about these block representations, but then the question is, how do you really store this in memory? And how do you operate on this with an actual program? And the consensus has been that you come up with this canonical representation for ragged dot. And the ragged part refers to the fact that instead of keeping blocks or sparse blocks along a grid, again, if we go back 2 slides, those gray areas are supposed to be empty. So you're not actually storing the data there. If you were to store, say, zeros, it would be highly inefficient. Memory is not locally accessible. Sorry, it's basically cache unfriendly, and you're also wasting a lot of space. So by far the most popular representation right now is to take these rows on the left-hand side matrix, just stack them in a single long list. This means that there's potentially can be a huge amount of imbalance along those rows. But on the right-hand side, when you're talking about the expert matrices, they're still structured. So they still have a particular static shape, and there's a fixed size of them. Now, your output is also ragged. So this packing along rows is essentially all you need. This representation has been super popular, and this is a very frequent way to represent ragged dot. And on TPU, it's pretty much the only way because it ends up being much more efficient. You're wasting no memory, and then with the Megablocks implementation, you can actually manage to avoid essentially all theoretically unnecessary work. So these rows are contiguous. You're storing the memory together. Um, I'm going to talk a little bit about how the efficiency works out here. So the thing to remember is that despite the fact that you have this weird fact representation, the amount of flops that you're doing is still as if you're multiplying two matrices together. The only dynamic part is that some rows belong to one of the matrices here, one of the expert matrices. And so the first question you can ask is, how efficient can we get? Can we get to 100% efficiency like a Matmul? Remember, the flops are the same. The flops for Megablocks operation are the exact same as for Matmul. And the answer is that probably not. That actually, if you're implementing a Palace program and TPUs are sequential machines that go through different block specs, different tiles, one by one, with the tensor core working on just one thing at one time, you can actually you cannot exactly adjust the tile size so that it's fully dynamic and divides these rows perfectly. So what happens is sometimes you're going to have a tile that has the boundary in it. Then what you have to do is both compute the top and the bottom separately, masking them out. This is a bit of a challenge. It is, however, a huge gain in terms of performance. So we could try to implement dynamic stuff. Even on TPU, what you could do, say, is you could have a powers of two loop over a block, and you could get an exact right block size that you wanted. The problem with that stuff is that it tends to not work very efficiently in practice. The ability to saturate the accelerator with work is also very important. So you have these two conflicting requirements essentially. You don't want to visit tiles too much, revisit tiles too much, like here when they span, but you also want to keep the tiles consistent so that the accelerator doesn't have any surprises. It can work very efficiently. There's some numbers how you can actually derive this, but I think it's cool is that you can actually create a model of this efficiency. So you take the probability of having to revisit a tile, and the larger your tile is, the higher that probability. It's quite high to begin with, but essentially you can think of what is the chance that I'm exactly dividing two groups with a tile, and the probability is quite low. Um, you can derive the expression for how many times you have to actually iterate. So if you go here, how many times do I have to visit this tile? This just once, the tile 2 I have to visit twice, so on with just one visitation. And finally, over here, because it spans again, I have to visit this tile twice. We can create this model, and if there is this quadratic model of optimal efficiency for a regular matmul with no dynamicism, you can see that for megablocks, the optimal tile size actually ends up being smaller. It's quite a cool find. This is the MFU efficiency. This is a bit of a toy model, like a mathematical model of the efficiency, but in practice, it kind of matches very closely what we see in practice, like empirically. Um, an interesting find is that if you add this tile revisiting stuff, you're making your accelerator visit a tile that spans two groups twice. And so the overall MFU, because you're still using the matmul as a reference for the number of flops, ends up being much lower. So here, the optimal one is probably something like 70% or 65%. Whereas for a matmul, you can very often reach 100% or extremely close to the theoretical hardware capability. There's also derivatives. Um, if someone's interested, this is a cool topic because ragged dot can be generalized actually, where you can express all the derivatives as ragged dot itself. Normally, when you're implementing stuff in an autodiff system, you end up with a forward approach, a forward pass. You have to implement a backwards pass, and then you never really know what happens if you try to differentiate the backwards pass again, because you would have to implement the backwards pass of the backwards pass. For ragged dot, all you have to do is implement two routines, ragged dot and then this transpose ragged dot, and you can differentiate them indefinitely. So it's actually a closed group, and all of these operations are similar to how you'd implement matmos, but this is maybe not immediately obvious. Um, but this again goes back to the paper, which is like if you can get a good computational regime for computing this stuff, it works really well with the modern autodiff system. It works really well with differentiation. If you're interested in scientific approaches that say take second order derivatives, this remains fully compatible. And all you have to do is implement two routines, this ragged and transpose ragged. If you're interested and want to read the source code for the JAX-up, these are often referred to as GMM and TGMM. The T is for transposed. The flops on all of these is the same. Um, there's one bit of a challenge though, is that as you're implementing this TGMM, you have to perform a lot of outer products. So essentially for each G, for each expert, you're constructing these outer products of left-hand side and right-hand side. Um, So let's go through the actual Megablocks implementation because this sounds a little abstract, but in reality, the kernel itself is very simple.
Can I ask you a quick
Um,
question?
definitely, yeah.
Yeah, so can you go back? Basically, so for context, we have the same thing in PyTorch. We use a little slightly different terminology. We just call it a group gem. And like we just call like 2D, 3D group gem would be like the forward pass where you have like the 2D input activations you kind of shown here, like they're kind of stacked with these like variable token group sizes. And on the right hand side, you have like the 3D expert weights. And then in the backward pass, I think you called it like transpose ragged dot. We just refer to it as like 2D group gem, right? Where the groups are now along the contraction dimension. And my question is, um, I don't quite understand how using this model, because what you're describing sounds basically just like a group gem, where the way I understand it, we're basically just parallelizing, num experts number of dense nanomoles, at least in the Cutlass kernel that we dispatched to, that's basically how it works. So I don't see how the mega block style like sparsity with the CSR block CSR format and everything fits into the group gem paradigm. I thought it was like an orthogonal paradigm, like way of approaching the problem, but it's from this diagram, like, it seems like very similar.
Yeah, that's a super good question. I think they are the same. So ragged dot is maybe used as an attempt to sort of generalize this algorithm or just use a slightly different nomenclature, but the computational routine that actually underlies this is the same. The big difference, I would say, and we have also Palace kernels for GPU, is that on TPU you really want to be operating with fixed tile sizes. And
Hmm.
so a lot of the differences in the actual implementation, and even when I'm talking about this, come really from analyzing this static tile sizes that you have to mask on the GPU. Because the SVM is much smaller, you end up with more loops, and so fewer of these large tiles. Like, right? To reiterate, which is TPUs have this very large VMEM that is counted in tens of megabytes, whereas on GPU you have much less to work with. And so um, I think that a lot of it has to do with hardware. On the Blackwell, though, the matmul units end up being bigger, um, so it's perhaps that this will convert at some point. But yeah, you're right. The loops save you in some sense for NVIDIA in the NVIDIA world.
Hmm. Okay, so just to clarify, in this, so what you're showing now, because there was a slide where you now start talking about modern mega blocks. So was
Mhm.
the original mega blocks the only implementation using the block CSR format, and now modern mega blocks is using this like group gem style approach? Is that a good summary or no?
Um, I think so.
Okay.
In the original paper, they talk about implementing a very general routine. They were also interested in, I think, developing Palace itself, so that they could have a very general routine that can represent any type of sparsity like this, which
Hmm.
is when I was talking about the previous scalar grid stuff. Later on,
Oh.
the modern, yeah, I think the modern here most accurately refers to the fact that, okay, we've done this research, but now we actually want to implement PMM very efficiently. So what specific representation do we pick on TPU and what specific implementation? Not just a general routine, right?
Hmm.
A specific algorithm that is called directly GMM and implements this particular representation.
Hmm. I also just remembered in the paper they mentioned something about how the block CSR with COO implementation also help represent not just like dynamic group sizes for the left hand side operand, but also for the dynamic like quote unquote like expert weight sizes. Um, versus like
Mhm.
in practice now, like for MOEs, like the MOE is like a static weight matrix, right? With like uniform sizes, right? It'll be like 8 experts by 8192 by 5120 or whatever. And so we
Mhm.
can probably get away with just the GMM with for this. But I guess if we were doing some kind of more researchy work where like each expert in the MOE layer had a different size, then we would probably need the original block CSR
Mhm.
COO. Is that right?
Yeah, I think it's a great summary.
Okay,
If you're doing
interesting.
research and if you're interested in this sparse stuff, there is first past examples for this, and second, um, the dynamic grids both on GPU, which are implemented slightly differently in the kernel languages, and on the TPU, these are the fundamental building blocks for those algorithms. Yeah, that's exactly right.
Cool.
Um,
All right, thanks.
so this is basically Megablocks, and they're trying to squeeze out the most performance out of it. So they abandon this generality in the routine, and now they move towards pre-computing specific metadata computation. It lets them do a couple things. First, You don't skip. In general, when you're doing numerical research, you can quite easily skip over blocks, and you're leaving maybe 20% of performance on the table, which, for chips MFU is quite good. Um, this was the scalar prefetch grid. When you're doing Megablocks and you're interested in the last bit of performance, you don't skip blocks. You pre-compute your lookup table, your map, in such a way that you end up only doing useful work. Um, the routine for doing so is actually quite large. So that they have a lot of comments, and but in the end, you end up computing a simple list. So it's a Python list or Python array of integers that has enough information to go from one tile to another. It's a flat lookup table, and your essentially just tells you exactly that this tile on the left-hand side should be multiplied with this group on the right-hand side. A lot of this work, a lot of heavy lifting on this for this on TPU happens in the memory pipeline. So the kernel itself ends up being very simple. It actually is not too dissimilar from a matmul. Um, so the metadata is complicated, but the actual kernel is simple on TPU.
Can I ask, sorry, one more question about what you just said? So we do something similar where we have CubeSum, like pre-computing, like offsets and metadata for the grouped gem. But you said something about how the resulting output of that is like a regular Python list, or so does that mean that there's like the device to host sync and the data is sent from, in this case, TPU memory back to CPU for dispatching the actual gem operations?
Actually, this is entirely then fits in SMEM, and so this is the memory in the TPU capable of conditional flow and capable of a dynamic pipeline.
Okay,
So
so there's
they're
no
able to
sync.
compute a map. Yeah, exactly.
Okay,
They're able to
okay.
compute a map for the accelerator itself. In some sense, NVIDIA's GPUs are also quite good at doing this themselves.
Okay, that makes sense. Yeah, because I was gonna say like one of the benefits of Group Gem is that we don't need to do that device to host sync and move all of our metadata to CPU to start dispatching gems. But then, so how did you said something about how Python list would just be on CPU, right? Or did I mishear?
Yeah. Um, no, that's exactly right. I did say Python list. No, I more like a Python list of scalars. If you look at the TPU SMM memory, it ends up looking like an array, but in reality, the only way to access and work with it is via a scalar indexing. So
Mm-hmm.
you think that it looks like an NumPy array and when it lives in SMM, but in reality, you cannot subselect elements 1 through 5. You have to
Mm.
individually go element 7, 8, 9. Yeah.
Okay.
Yeah, it's just a array of scalars.
Mhm.
But these are it fundamentally all stays on the device is the main
Yeah.
takeaway, right?
They're on
Okay.
the device, uh, but in this special memory, yeah.
Got it.
It's
Cool.
very restricted in what you can do, but yeah, highly dynamic. So the TPU itself has this conditional flow to it. Um, but yeah, that is essentially the takeaway: is that the Megablocks implementation, when it's fully optimized for TPU, ends up doing most of the heavy lifting in a memory pipeline. The kernel itself is just matmos and a little bit of masking. I think that's quite different to GPU. Um, okay, so when it comes to the MOE layers in JAX, we have this global array view with some sharding. So you end up with a two-stage matmul, a gate projection, map projection, followed by a down projection. In JAX, we shard this. So how do you take control over this? JAX has this escape hatch hierarchy where you can start with very simple programs, just NumPy and jitting your result, and it should run very fast. This is again XLA level, not quite on the MOE side. You can add sharding hints, but when you're writing kernels on TPU, and if you want to experiment with this, if you want to do the same thing on GPU and JAX too, it's also true. You often have to go a little deeper. So the two things that you have available to you is shard map, which is the per device view. When you drop into a shard map in JAX, you're essentially trying to start computing from the perspective of an individual device. If your array started 1000 by 1000, but it's sharded over two devices, then the array now looks like it's 500 by 1000 under shard map. And then for Megablocks, this is the TPU Megablocks, the GMM implementation in Palace TPU. You also need the Palace kernel. So if you want to start experimenting in JAX specifically on new kernels and new numerical research for this sparse and dynamic stuff, you would typically use a combination of these two. You'd first drop into a shard map and then do a Palace kernel that computes only stuff on a single device. SharmMap itself has a bunch of calls that lets you do communication. You can also do communication in Palace, but Imgen was also working on this. It's quite nice that a lot of the communication can be handled by the compiler. You can communicate in Palace. It ends up often being difficult to implement, and it doesn't exactly buy that much more performance than just doing it in SharmMap itself under JAX. So um, this is basically a small plug for JAX, for how hopefully easy it is to express an MOE like this. And so the way you would implement an actual layer, I'll maybe go through this because it's really simple. I'm sure people are familiar with this. You would first prep the thing. So this is before the shard map. You would define some helper lambdas. You'll route the tokens so that you actually know which tokens belong to each expert. You would define, and this is the important step for the shard map, the in specs and out specs. So how the arrays should be sharded on input and how they should be sharded on output. And you can define some constants for the shard map itself. When it comes to the actual routine, first sort the indices so that you know which rows have to be stacked on which. Your token routing in general for a general model is not ordered in any way, so the last token can end up at position 2. You then have to gather the tokens, and this is interesting. GPUs are quite good at this. On TPUs, what we have is we have the Tensor Core, which is doing matmos, but we now also have the access to, thanks to the recent compiler additions, the sparse core. So sparse core was explicitly designed for it to be able to perform operations like gather and scatter efficiently, so that can rearrange rows. And this is what we need to do. We can get the group sizes via bin count. This is not quite the metadata computation for GMM. This is more just being able to represent that the ragged dot representation. You then have an up projection and a down projection that are fairly simple. You weigh the output tokens. And the interesting part here is the shard map part, which is how you actually communicate the output. You get access to explicit collectives, and so you can do the computation per device. And this is an example of a tensor parallelism implementation. And then in the end, you actually issue these collectives here. These are collectives issued on the critical path, so you end up with a result which you then communicate. It's really cool research and really cool experimentation if you either want to do this in micro batches, so you can try to pass through this routine in micro batches, or if you're implementing other algorithms. A ring attention is a great example where you're computing partial results and you have to do communication as overlap with computation. Okay, so that was MOE. I also have a bit of a quantization because that's also something we've been working on recently. The way you quantize matmos is on most hardware you get about a 2x speedup. NVIDIA did amazing research on floating point 8. So floating point 8 is this format which, it's an IEEE format, but it's super low precision. It somehow still ends up working extremely well. So it's basically the new direction, I think, for a lot of these heavy machine learning workloads, where matrix multiplications, especially, maybe not stuff like attention, those tend to be somewhat sensitive numerically, but definitely any matrix multiplication and any MOE ends up being pushed towards the quantized version. This is maybe too much detail. People are familiar with this. I think for full channel quantization, we end up often multiplying two matrices where only the scales, the individual scales, are scaling the non-reduced axes because you don't want the scales to interfere with your actual matmul. The matmul should be performed directly in the low precision format. So if you want to do an FP8 matrix multiplication, you have to take just the quantized array and multiply that. You cannot upscale it beforehand because that would not let you make use of this fast matmul unit. So yeah, for compute bound, you have to do this, where you actually matrix multiply just the quant part, and then you just scale by the scales. For HBM bound, which might also be interesting, this is for inference, it is actually perfectly okay to scale this stuff before or after the matmul. So you can perform a matrix multiplication between a BF16 and FP8, and it does not give you the speed up of a matmul, but if you're memory bound, it does give you the speed up of the HBM bandwidth, reading in much less data. When it comes to subchannel quantization, it varies. Both GPUs and TPUs, the way they often deal with this is that as you're implementing Palace kernels, you or any other kernels, you tile your computation and the result. And so if your tiles are small enough, do not have to span individual scales along the reduction dimension, along the subchannel quantized dimension, then you can actually just do that. And here you would load a scale that is specific for the tile instead of a scale for a full axis.
That's a good question.
When it comes to yeah, yeah.
So does TPU have, because like on GPU we have like for example a specific like FP8 tensor core. Does TPU have same kind of
Mhm.
specialized tensor core or is it generic?
TPUs have int8 unit that is twice as fast. You can actually look up the flops and they end up almost exactly twice as fast.
In
Um,
sorry, go ahead.
yeah, int8.
And so does it support FP8 though? Can you do FP8 gems on the same whatever it's called is it called MXU in TPU?
That's right. No, in general, this is going to be hardware specific. So the way the chip was designed, it'll only be able to do this.
Interesting. What about next generation? Are they planning to support? Because it's nice with floating point, like you can, it has like the exponential range, whereas like, in date, it's like there's just like static, like discrete boxes of
Yeah,
uniform size, whereas like floating point, we have like the exponent bits, and so you can represent, it's kind of more like like a probability, like a Gaussian distribution or something, it's like exponential in nature. Does that make sense what I'm saying?
yeah, yeah. It makes a lot of sense, and yeah, you're exactly onto something. NVIDIA's research on FP8 and the representation and the numerical accuracy is super cool, and yeah, I think FP8 is seems to be much better than int8. The TPUs so far supported int8, but um, hardware evolves all the time, so we'll see.
Hmm. What about even lower precision? Like, is there any 4-bit formats supported on? Like, NVIDIA has like like NVFP4, MXFP4 now in Blackwell. Is there anything in TPU land going this direction?
So some of it is software support, some of it is hardware support. In general, in MXU, will be able to do, at least on TPUs, only two D types. So, and the TPU, it's BF16, BF16, and int8 and int8. Um,
Hmm.
the other types, lower precision, usually are supported via software. So the compiler will issue these casts plus MXU operations. It won't be any faster, but they might, for instance, speed up HBM bandwidth constrained workloads.
I see. So it's sort of like virtualized or emulated in a way by the software.
Yeah,
Okay.
that's right.
Cool. Okay.
They
I think,
they would save memory. Would they save? Was that these virtualized the fake data
yeah,
types?
yeah, that's right. They both save memory unlike in HBM, so your neural network takes up less space. They also save HBM bandwidth, or they could. It's a bit of a hard problem actually. When you talk to compiler engineers, it's not easy to feed the matrix multiplication unit. Um, so for some applications, if you can get your matrices large enough or square enough, the computational complexity grows with n cubed of the tile that you're multiplying, but memory grows with n squared. And so if you can optimize for that, you can sometimes get faster results. But in general, I think it's a compiler and hardware challenge to feed these units with these lower precision formats. All right. When it comes to quantizing ragged dot, this isn't dissimilar from Matmos, but it's sort of good to keep in mind is that you can utilize basically the same quantization. You can use full channel, you can use subchannel. The ragged dimension is often the one that doesn't participate or the ragged dimension is the dimension that does not participate in the actual matrix multiplication. And so same lessons apply. When you're doing research on quantization in Matmos, you can quite quickly generalize to GMMs and TGMMs. The one thing to keep in mind, though, is that the reduction axis actually changes. Um, in practice, when you're trying to make neural networks run faster with quantized training, the big challenge is that the quantization itself requires first computing your range and then dividing the actual tensor so that you can cast it then to a lower precision. Both of these operations are vector operations, and both Blackwell and TPUs they just don't have that many vector units. On GPU, these are the CUDA cores. On TPU, this is the vector unit, and these tend to be actually much weaker than the matrix multiplication units. So when quantizing, when doing training, quantized training, it's always really a challenge to get your tensors to be quantized fast enough. And so when you're doing the forwards pass, one axis is the reduction axis, the k-axis. When you're doing the derivatives of the left-hand side and right-hand side, the reduction axis changes. That usually means that your scales change. They should be along a different dimension. Again, quite interesting numerical research. For instance, DeepSeek used a square window scaling. So in that case, they use a window of 128 by 128. And at that point, you're basically subchannel quantizing along both axes. So when you're differentiating your reduction axis or the challenge of performing matmul subchannel quantize doesn't change because your k axis and your n axis are both quantized subchannel. It's it's a good question. It'll very much depend on what type of training you want to do, but something to keep in mind when
Oh,
quantizing matmals, but also GMM in this case.
I had this question that this
Yeah.
quantization is based on the image, like downsampling, something like that.
Uh, you'd usually the typical approach. So you actually
Like
have a lot of freedom. Yeah.
like for example, if this image is like 32 bits, if you I, like if there's this formula formula like 2 raised to something like that. I didn't remember about the quantization. It's only about like downsampling. Is that what it is in here?
It's somewhat similar, actually. You are often moving between the two
Like
types of representations, like Daniel was saying, which is the floating point representation and the integer representation. And so there is some complexity there, right?
okay. I was related talking about like computer vision model like that, like
Hmm.
CVT. About that, like that is comes under like quantization, like downsampling, reducing this 32 bits into 8 bits like that. So is
Yeah,
this
it's the
the
same
same thing
numerics.
it does? Okay.
It's the same numerics. The additional challenge here is that you often work with floating point types, which you can
Oh,
actually look this up, but the line number distribution of these points is not even. It's not like for integers. Um,
Are you asking like about channel expansion and channel reduction?
yeah, yeah.
Yeah. I think this is kind of is a different topic. This is just about quantizing, but I think the math is can be similar.
Okay.
nice. When it comes to matmos and specifically Megablocks in Palace, the way Palace works is I was alluding to this, but it essentially has a memory pipeline. GPUs operate somewhat similarly, but you would often express that memory pipeline in the kernel itself, just because NVIDIA is so good at making the hardware units operate together. On TPU, you only have a single hardware unit. So getting the memory pipeline sort of right ahead of time is an explicit topic on TPU. You'd have blocks in HBM that you have to load into VMem, and have to perform computation on it, and then store the results. Again, on NVIDIA GPUs, you can do this whole process in the kernel itself, and then rely on the hardware allocating resources to SMs, and then blocking the ones that are blocked. On TPU, you design this memory pipeline explicitly. This is why the scalar prefetch grid works so well, and this is why you would often talk about these memory pipelines literally correctly. And so this block indices really help get your new data to be in memory as soon as possible so that you're never blocked. When it comes to writing a matmul on TPU, the kernel itself is extremely simple. So this is what I want to show you very quickly is that, to be honest, GMM on TPU is not very different. The only thing that gets added is masking. And so this two-line function, that def matmul kernel, is almost exactly the kernel that you write for Megablocks. The entire magic or the bits of complexity comes from the memory pipeline. So in the Palace kernel, you would define this inspect, which have the lambda, and this is the lambda over the memory pipeline. Again, this is an example for a matmul. For Megablocks, it's not entirely different in as much as you go from a lambda that goes over ijk to a lambda that uses those ijk to index in your metadata pre-computed lookup table. So yeah, I just kind of wanted to show you that I think the TPU implementation of GMM is extremely clean. That if you look at the source code, some of it is bookkeeping, but the computational core of this is extremely nice. It's extremely easy to reason about. I wanted to also plug a package I was working on. In practice, when we try to get these kernels to actually run at 100% performance, 100% theoretical MFU, because you have the problem of block skipping, you really need to tune. You can run a tuning example on a matmul, or I mean, we do this on the ragged dot as well. The reality is that it's extremely difficult to guess the tile size ahead of time. What happens is because you're not just doing matmuls, you're doing matmuls and you're masking the ragged dimension. So a mask is a vector operation, and a matmul is obviously the MXU operation. This work has to be parallelized. Um, so what you're doing is that you're taking chunks of your matrix, the one that you already loaded into VMem or SMem on GPU, and as you're computing your chunks, you're masking the chunk you already computed, and so on, like a ladder of sorts. In Palos and TPU, we have a compiler that does this. It's super useful, but that unfortunately also means that it's very difficult to guess which sizes are the most friendly to the compiler. So I would highly recommend whenever you're writing Palos kernel, just run it through a tuner. It doesn't have to be this package, but a for loop really helps. I know that Adam Pashka, when he was developing the Mosaic GPU, say the flash attention initially, the language itself, the Palos dialect itself, he was doing a lot of tuning. It's very difficult to get. Kernels tend to be much simpler than writing CUDA directly, but you also have to make sure that you tune the tile sizes. This is one maybe like a practical advice is that as you're writing a kernel, it really helps to parameterize everything, the static parameters. So for a matmul, it's the tile sizes, because then later on, you get all these knobs that you can adjust, or you can use an automatic tuner to adjust, that you can really get the best performance. In this example, I'm tuning a matmul, and the worst result for the worst tiles, even though all these tile size choices are very sane, like all of these tile choices are very reasonable, the worst result is 3.3 times slower. It's just very difficult to guess. Um,
Can I ask a question on that?
yeah,
Why is this it sounds like a separate package? Why isn't this just included in the like Palace itself or yeah.
yeah, it's a good point. Palace is a language itself, like, if you're talking about what is core Palace, tends to be somewhat general. They talk about the memory movement, they talk about the actual compute on the TPU. So it's probably something that's a little more meta. And a lot of people use for loops, and for loops work quite well for a lot of applications. Um,
Daniel, I have a
Hmm.
question. Does Triton have a similar utility?
Yeah, that's why I was asking is Triton just has a decorator. It's called like at autotune and you just plug in your configs like your list of block sizes or there's actually my next question was a follow-up, which is there more than just the tile sizes you can tune? Because like for example in Triton there's num warps, which is like the number of warps per do you want to
mhm,
handle per block, and because you could just naively have if you have a block size of whatever 1024 1024 divide that into 32 threads per warp and then just use the full amount, or
mhm.
depending on your specific workload you're trying to do. Maybe it makes more
Yeah,
sense to use fewer warps or more warps if you want to swap between them for like hiding memory latency
yeah.
or whatever. There's also like num stages for pipelining the memory movement. You can tune that. So I was just curious, A, like why it isn't in just natively included in the kernel, the DSL package, and then B, is there more than tile size you can tune?
Yeah, that sounds like grid. What you the num warps?
No, it's not grid.
Yeah,
But
it's a
yeah.
little different. Uh,
Isn't
it
it the
makes a
product
lot
of
of
the
sense.
grid?
No, no.
You can, yeah, you can assign multiple warps, especially in Blackwell and the new GPUs, to a particular kernel. Lets you use warp group specialization. I think the answer, the two questions. One is why isn't this included? I'm not sure. It'll probably help. Iron definitely has its own tuner. Sorry, one sec. I'm sick a little.
No worries.
Yeah, I'm not sure that the Triton additional knobs are actually in the API that they exposed, but Helion, which is a higher level kind of BSL for making tile-based kernels, which Meta are working on, that uses Triton internally, but because it uses the dialect directly, it exposes a lot more of all of those
Mhm.
knobs, and that's how it actually gets better performance.
I can also comment on the TPU comparison to this. This is exactly right. In some sense, on a TPU, num stages say if you set it to 2, it's essentially always optimal. The hardware ends up being a little simpler, which is why on GPU, why you might want to tune num stages, it's just set it to 2 on TPU and it's optimal.
Hmm.
If you take a look at Mosaic GPU, um, so say Raggedot on GPU, there's some cool examples that Adam wrote for the Blackwell Raggedot. There is a lot more knobs. So I think the short answer is that this is just hardware specific. There's just more knobs on the GPU.
Interesting. Okay, thanks.
I also had a question that I forgot to ask earlier. Uh, for TPUs, don't we try to keep the I don't know if it's just specific. I think it is specific to the right operand. The dimension should be divisible by the lanes, right? Robert?
Um, PU definitely. So when you're performing operations in TPU that are not conditional flow, they all live in VMem, which is the vector memory, and that is laid out along physical lanes and sublanes. There's definitely a restriction on TPU. It's 8 by 128. The last two dimensions have to be this size.
Yeah.
If you
So
yeah.
so does that affect the grouping that you do for MOEs?
Yeah, a little actually. So what happens is the rows, though, usually are along the second minor most dimension, and so it's only a multiple of 8. It does. So you cannot go lower than 8, which is why, in theory, on TPU you'll always have some amount of tile revisiting. But if you look at that performance curve, it's rarely there. Like the optimal point is rarely there. The 128 dimension, that's more restrictive, right? Because I mean it's bigger, is usually along the reduction axis, so it's usually not a problem. Also, like Daniel was saying, the right-hand side tends to be in modern MOEs much more structured. There's much less sparsity, or there's no sparsity there, and the static shapes are entirely static. Um,
And this restriction is for the right hand side, right? But on the backward pass, is that still okay, or yeah?
It's still okay actually because the sub selection that you do, the problematic one is TGMM, which is the outer products for constructing expert contributions. There you end up with the also selecting along sublanes, and the multiple there is 8. The DPU has that restriction, by the way, but it's also not restricted to powers of 2. So I could have 384 because that's 3 times 128. Uh, but
So
yeah,
can you
in
repeat the last point? What you said, the GPU also has that, but it's not as restricted because
the TPU actually. So
TPU.
TPU is restricted to 8 by 128 in the last two dimensions, but this any multiple of this, even prime numbers and such, work.
Yeah,
So
yeah.
these are not climbing powers of 2. Yeah. Um, But yeah, for your comment about MOE, yeah, modern MOEs don't really suffer from any of this because every time you have this highly varying dimension, the increment is very small. It's 8. In practice, in hardware, you often want to perform products that are more or less square. If my reduction dimension is 2000, I kind of want to be working closer with a tile size of 500 or 1000 than a tile size of 8 by 1000. Because that is very no square, and the hardware it works out much worse. Um, Unfortunately, it just needs more vector operations, two matrix multiplication operations, and that ratios. You have to pay attention to those ratios. MXU is much more powerful than the vector unit on modern accelerators. And that's the point that applies to both TPU and GPU. Yeah, that's all I had. Thanks
Cool.
so much for the discussion.
Yeah, sorry, I actually have one more question on this slide. Um, if you have a minute. I see here you
Yeah.
say, at least it looks like this JAX implementation of GPU Ragadot has no WGMMA instruction. Why would that be?
All right, I just want to distinguish. There is work for people who work on GPUs directly, and there's the stuff that I'm sort of experimenting with personally. What
Hmm.
I wrote is in the Pallas Triton dialect, which is a fairly old implementation of the Triton in Pallas. It's just that my personal implementation is quite bad. It's not that this is impossible, or it's not that there aren't better implementations.
Okay.
I'm linking it here because I think that's the fairly simple one. So it's like a minimal one. It'll probably not let you pass 40% MFU, maybe 60% on Hopper. That's as much as you can hope for. Um, for
Hmm.
GPU research, I highly recommend Mosaic GPU, which is the
Hmm.
new dialect in Palace. Yeah.
Hmm. Okay. Is it a implementation thing or is it a Palace thing? Before not talking about Mosaic, but specifically Palace and your implementation, I just don't understand why the compiler would not use WGMA. If you have like a TL dot um, with the
Yeah.
appropriate D types in the appropriate places in the memory hierarchy, shouldn't it just automatically compile to that PTX instruction?
It should. It's a matter of these indirections. You end up writing Python that gets compiled to Palace Triton dialect, that then gets compiled down to Triton. You just might end up losing something along the way. I haven't tested it exhaustively on, say, Blackwell.
Hmm.
Um, I think the major trend that everyone's doing right now is to try to do these things more explicitly. If you want a TC Gen 05, you just issue it directly,
Hmm.
which is why I really encourage people to take a look at a Mosaic GPU, because you do those things there very explicitly. Um, so
Huh.
it's much more sane to tune those things because you issue a particular instruction that you want rather than hoping for the compiler to do it for you.
Okay. Interesting. Cool. I'll probably take a look at the Mosaic implementation just out of curiosity. Compare it to what I've been doing in CUDA and Cutlass and Triton and all that.
Yeah, there was a new tutorial that I shared in the chat that got released like last week or so,
Hmm.
especially for Blackwell. Yeah, it claims to be more efficient than Cutlass
Really?
for
Yep.
for
That actually is,
MatMo.
that isn't even wait, just regular MatMul or like group MatMul? Group gem.
Regular MatMo.
Okay, interesting. Yeah, strangely, the Cutlass kernel that we use as like a starting point, we actually don't get like a high percentage of peak theoretical T-flops, which is surprising. At least,
Mm.
you know, yeah, I don't know. It's I shouldn't say much more yet, but I'm just there's still some work to be done there, I guess. But I would be I guess not super surprised if somebody managed to have a better implementation. Cool. Yeah, I found this
Yeah.
super interesting. Sorry, you're gonna say something?
I just wanted to add a +1 for the tutorial. I also
Hmm.
saw it recently. It's really good.
Okay, cool. I'll check it out. Awesome. Yeah, this is very particularly interesting and topical for me because I happen to be working on almost exactly this in my current job. I'm giving a talk at PTC next week, PyTorch conference next week, actually on MXFP8 MOE training, where a large part of it is quantized group gems, specifically like MXFP8 quantized group gem that's like differentiable for the forward backward pass, and on Blackwell with their specific requirements about the scales being in like this block swizzled format and needing to live in TMEM and all this stuff, it gets quite uh, interesting and complex. So that was actually thinking this would be a good follow up topic for next week or just whenever we have time and then maybe 2 weeks from now. We could compare what's going on in GPU land with everything you've discussed today, which mostly TPU land, but a little bit of
Mhm.
GPU as well. Um, and yeah, really interesting seeing how things are working on the TPU side. I thought that the JAX implementation you showed of the MOE layer was very clean. I always find Jack's code to end up looking like very nice compared to PyTorch sometimes. Um,
Yeah,
so very cool stuff. Yeah, this was an awesome presentation. So I really appreciate you volunteering.
Yeah.
great. Yeah, thanks.
Plus,
I'm
thank
curious
you,
about your
Robert.
talk. Cool. Yeah, thanks everyone. Yeah.
Awesome. Cool. Well, yeah, if you feel free to share the slides if they're public or shareable. I saw those people in the chat wanting to go over them. You can share them. But yeah, with that, I guess I
Yeah.
can end the recording.